This is lecture 28, the final lecture in friction, and actually the final lecture for the quarter. So this is dealing with what's called belt friction, which is a subset of the friction that we've been talking about. And it's not a difficult concept. It's just something that you may be exposed to in the future. And so I wanted to throw this in as kind of a last item in our world of friction that we've been covering. So belt friction or rope friction, however you want to describe it, is the friction that's produced when you wrap a cable or a rope around a cylindrical object. And so if you think of like a horse, you can wrap the bridle rope around a pole or a hitching post, whatever. And if you wrap it around several times, then it actually is quite difficult for it to be pulled. Another thing you could do is if you had to lower someone off a cliff, you could wrap the rope around a tree several times, and you'll notice that the friction that's produced by the tree would greatly reduce the amount of effort that would be required to lower that person. And that has to do with the friction as it due to the contact between the rope and the circumference of the actual cylinder in which you're wrapping it around. So the equation itself is actually fairly simple. I put these two images here, A and B. These are directly from your textbook, but the one on the right is more telling. So if you think of a small segment of an angle theta, you have what is a normal force going up, and you have a friction force going to your left, and you assume that the higher tension is going to your right. So probably a better way to explain this would be looking at it this way. So imagine that you're pulling this direction. So if you're pulling it that direction, then the tension 2 is going to be greater than tension 1 because you have to overcome the friction that's created on the contact of the surface. So up until this point, we've assumed that anytime you had something like this, it was smooth, there was no friction. So this is to account for when there is. Now, it turns out that if we take dt, the change in tension with respect to tension, that is going to be equal to the friction coefficient times a small amount of d theta. And the full derivation's in your book. But the simple derivation is that then if you take the log of both sides, you end up with something that looks like this. You end up with T2 over T1 equals E to the mu static or mu kinetic times beta. So what that represents is beta is the wrap angle, or how many times you've gone around the object. So for example, if I had a circle like this, and I had a circle like this and that, and this was my T2, this was my T1, then this would be pi, because it's half circle. So pi would equal beta. So what I could determine then is the difference between the tension here and the tension there. The ratio would just be equal to T2 over T1 would just be equal to E to the mu static. And let's say that we had a mu static equal to 0.2. If that were the case, then what we could do is we could take 0.2 and pi and take the exponent. So what we'd end up with is 0.2 times pi, and we end up with a ratio of 1.87. So that means that if there's 100 pounds hanging off of here, it's going to take me 187 pounds of force to pull this down here. Okay. And that's really all there is to it from a standpoint. Now, let's look at a quick example. So we can look at this any way we want, but we could say, for example, if we have 50 kilograms hanging off of here, then there's several things we could say. What is the mass required? So let's do first one. The mass required to lift the 50 kilograms. All right, so what does it take? So because this is the side that's going to have to overcome friction, right? Because we're going to have to pull this down. It's going to have to overcome the friction here and the friction there. Then this side is going to be the T2. This side is going to be the T1. So what we end up with then is we say T2 divided by 50 kilograms. And it doesn't matter if we multiply by gravity because it's a constant. And that's going to equal E. And in this case, we're given friction's 0.3, so 0.3. And then how much angle is there? Well, there's this and that. So it's basically a quarter, and a quarter is a half. So otherwise it's pi. So if we calculate this, multiply both sides by 50, we end up with the tension 2 is equal to 128.3 kilograms. So it simply means that it would require 128.3 kilograms to raise the 50 kilograms. Now, another way we could look at this problem is if, say, we're trying to lower the 50 kilograms. So let's say you're trying to lower this load down like a hacksaw ridge style. You're trying to lower someone down, and this is how you have it set up. How much, for one, how much would you need to keep this in equilibrium? And so if you just wanted the person to dangle there, how much would you need? So in this case, friction's working with you because you're trying to prevent this from moving down. Before we were trying to move this way. So friction was working against us. So friction's working for us, then we switch. This becomes T2. This is T1, right? So another way to look at that is we can say to maintain equilibrium, then what do we have? We have T2, in this case, equals 50. And then we're going to say E to the minus pi over 0.3. So by adding the negative sign, all I did was flip over T1 and T2. So I could have just as easily put 50 on the top and then put my unknown down here. But by adding the negative sign, I can leave it that way. So now if I calculate this, it turns out that in order to maintain equilibrium, this tension only needs to be 19.48 kilograms. So not really too much, okay? So that's that. Let's go back to this. So that was the example I just did. I showed you the two masses. Kind of got ahead of myself, but I think it's pretty self-explanatory what we're doing. Now, this is another example that you could do on your own. It's not super difficult, but in this case, what it's asking for is what would you, there's actually two questions. It says first, the smallest weight W for which equilibrium is maintained. So you have to figure out how do you maintain equilibrium in it. And then the second part is if you were to rotate pipe B counterclockwise while pipes A and C remain fixed. So now you're given both static and kinetic friction. So you're going to need that for this problem. So there we have our 50 pounds. Now, so if we're going to determine, this is actually part B, so let's do, find my piece of paper. Let's do it with this. So let's do part B first, and then we'll come back to part A, because part B is actually more challenging. So in this case, we're going to ask, what would it take to lift this? All right, so find the largest W that can be lifted. So B is going to rotate counterclockwise. C is going to remain static. A is going to remain static. So that means that these cables are just going to slide across. So we're going to use the kinetic friction for here and here because they're just sliding across the object. Here we're going to use static because the assumption is that the cable just stays on the same location here. So if we let's look at the first, we'll call this A. Then we'll start off with the first one. So if we draw this down there, there's the 50. Draw this over here. And we're going to call that tension AB. All right. And then we're going to, so this is going to represent our T2 here. And this is going to represent our T1 here. Then we're going to draw the rotation around here. Okay, that's going to represent B. And that's going to be representative of TAB. And this is going to be TBC. So again, this is going to be tension 1. This is going to be tension 2 because of the way we're lifting it up. And then finally, we have this going down here and this going here. This is my C. And that one we're going to call T1 the weight. And this is going to be T2, which is tension BC. All right. So again, we're trying to pick it up. So because we're trying to pick it up, the weight is going to be our, we're going to have to overcome friction here and here and here. Now, what's the next step? So in this case, we just look at what do we have? Well, we know that in this case, beta is pi over 2 because it's 90 degrees. And our friction coefficient is kinetic because it's sliding across, so 0.2 mu kinetic. In this case, we have beta equals pi, it's a half circle, and we have mu static, which is 0.25. And then here we have beta equals pi over 2, and mu kinetic is 0.2. So let's start off. We can write our equations then. We know that 50 over TAB equals 0.2 e to the 0.2 times pi over 2. All right. And then we know with this one, we have TBC over, since this is T2 and this is T1, we can write TBC over TAB. And that's going to be equal to, that's equal to e to the 0.25, sorry, times pi. Sorry, so it's kind of small. So we have 0.25 and pi. And then lastly, we have TBC over W. And that's going to equal 0.2 times pi over 2. All right. Now, you can actually simplify this. Now, one thing you can do is you can go ahead and multiply all of these out and add them together, or what you can do is you can actually, so you can solve for TAB here, plug it in here, solve for TBC here, plug it in there. Another way to do it is to separate them out, because you know that each of the sides have to equal each of the other sides. So another way to write this is 50 over TAB times TAB over TBC times TBC over weight. Now you'll notice that I flipped the TAB and the TBC. So I'm going to have to count for that, I get to put a negative sign here. So all that is going to equal e to the pi over 10. Now where did I get that? 0.2 over 2 is the same as 1/10. So if you take 0.2 over 2, that's basically 0.2 over 1 would be 1/5. So over 2 is 1/10. So that's what I got. Then you multiply that by e, and again we flip this a, b, b, c. So we're going to say minus, and that's going to be minus pi over 4, and that's just 1/4 pi. And then we're going to then multiply this by e to the, again, pi over 10. Okay, so we end up with then this cancels with this with this, and we end up with 50 over w equals e to the minus pi over 20. And so we end up with basically 50 over 0.8546, which equals w. So w equals 58.5 pounds. And there you go. So that's how you do that. So what that would say is if you were to slowly move it. Now, the other first part, if you want to, and I'll let you do this. I think I've shown you this, so I think you could do it on your own, but just if you want to try, the minimum weight that you would need to maintain equilibrium for part A, that equals, so the minimum equals 10.39 if you want to try that. So I'm not going to go through it here, but minimum is 10.39. So that's how much weight would be here so that this whole thing wouldn't go sliding that way. And again, to do that, you would say T1, T2, and then this would become T1, that would become T2, this would become T1, and that would be T2. Okay? All right. So hopefully this is making sense. It's just one minor part. So let's go ahead and look back. So let's go through a couple of more practical applications of this, in the sense is that what are we actually solving for? Go ahead and read this problem. You have the system shown measures the output, and so what you have is each spring had reading 14 pounds when nothing's going, and then when you start the rotation using at constant speed with a 105 inch-pound couple, that's to keep it rotating clockwise. And so they want you to determine the reading on this each scale. So how does that change, and the flywheel spinning, when the flywheel is spinning, and what is the kinetic coefficient of friction. So big assumption in this problem is that the belt doesn't stretch. We assume it's perfectly rigid. So as you can imagine, if this thing is spinning clockwise, then ask yourself, if this thing's spinning clockwise, which one do you think is going to represent the tension 1 or tension 2. So think about that for a second. So here's a drawing of it. We have tension A, tension B. So if it's rotating this way, that means it's going to be, in essence, the friction is going to be pushing this up and pulling this down. So it makes sense that tension B is going to be your T2, and this is going to be your T1, since tension B is going to be greater than tension 1. So imagine this rotating, pulling down on B, pushing up that. So the scale is going to be slightly different. So we know that we have the 105 inch-pound clockwise moment. At rest, we know that equals that. So we want to find this, this, and this, and we know our beta is equal to pi. So first equation, we know TA plus TB has to equal 28 pounds. So regardless of how they change, we know that the net tension has to be total 28 pounds. We just don't know how much is carried by which. We also know that TB times, so one of the things, the diameter is 18.75, so we can also determine what the effect of the moment is. So we know that TB, since it's going counterclockwise, times 9.375 minus TA times 9.375, and that's just the radius, has to equal 105 inch-pounds, right? And so that then, if we simplify that, it means that TB minus TA equals 11.2 pounds. So we have this equation and we have this equation, and so we can add them, which is pretty easy. If we add the two together, we end up with minus TA plus TB equals 11.2. TA plus TB equals 28. Those cancel. 2 TB gives us 39.2 pounds. And so TB is equal to 19.60. Therefore, TA is equal to 8.4. All right. So now we have those two values. So the last thing we want to know is, what is the kinetic coefficient of friction? So now we have everything we need, right? Because we know that T2 over T1 equals E to the mu kinetic beta. So we know that TB is so we can say TB, since we know it's the greater, over TA, or equals E to the mu K times beta, which we know is pi. So effectively, what do we get? We get 19.60 divided by 8.40. Take the log of both sides, equals mu K times pi. So that's how we solve for it. So I just substituted in the values TB, took the log, got rid of the E, have that, divide both sides by pi, and we get a mu K equal to 0.27. All right. Sometimes you'll see friction coefficients with a third, but that's really silly. You can never, friction coefficient really is never more accurate than two places, for mostly sometimes either one, but 2 is fine. So I know technically the sig fig rules would say add another one, but in terms of friction coefficients, it's okay to leave it at 2. Okay, so that's that problem. Hopefully that made sense. Let's go ahead and do another one. So slightly different one here. Now in this case, what we have is a belt that's wrapped around a flywheel. So the flywheel spins, and as you apply pressure to the belt, it's going to slow down or even stop. And so the idea with that is how do you determine the, actually sorry, I just looked at this. Yeah, how do you determine the tuple? So to maintain constant speed. Sorry about that. And so they're given everything you need. You have mu k is 0.25. You're given that you have basically 3/2 pi. So you have 270 degrees of contact. And then you have this 100 Newton force applied. So just like any other statics problem, you're going to start off by sketching it out, and then you're going to look at individual pieces. So similar to what we did in chapter 6. So we start off, we have our drawing. So we know our radius is 0.15. We know we have the center E, given the radius. We have this contact at B, contact at A. We know that they're 80 and 80 equidistant, and then we have this 320 from here down to the applied force. So again, we're trying to find the moment, right? We're trying to find the moment. Now, one thing on this, let me go back real quick. So don't worry about this last part. To show that the same result is obtained if the flywheel rotates counterclockwise. So it turns, it's one little step, but it turns out that it doesn't matter which way the wheel rotates. You're going to get the same moment required because of the symmetry, and it just turns out that way. So that's not something I would ask you on a final, but mostly I just want you to understand is how do you go from the belt friction to the moment, because this kind of then ties everything together that we've been talking about. So we start out, let's just look at the disc itself. So we have the disc. So we know that in this case, beta is 3/2 pi. And we know that in this case, we can write T2 over T1. Now, because it's rotating clockwise, it means it's going to be pushing T1 over and pulling this one down. So that's how we get the respective T2s and T1s. So if you can see that right away by looking at it, that's going to help you a lot, because you can see how this is pulling, and so it's working against friction. Friction is actually helping this by actually pushing it. So it's going to be less value than that. So we know that's T2, that's T1. We're going to say that that's equal to e to the 0.25 times 3/2 pi. So we're going to get a ratio of T2 equals 3.248 T1. All right. And so that's our ratio. So now let's go on and let's look at the actual diagram. So there's our object. Now we know that we have the applied 100 newtons down here. I'll try to keep that so we have the dimensions here too. But so in this case, what we're going to try to do is we're going to try to solve for our tensions. And so we're going to sum the moments about C to see what we can do. So we know that T1, both are going in the same direction. So T1 plus T2 times 0.08 or 80 millimeters. And then that's going to be minus 100 newtons. And then its distance was 320 up to there. So, or 0.320. Okay, so slower again. So we're summing the moments about E. We know that 80 and 80 are the respective distances from C. So we know it's 80 that way and 80 that way. and then we know it's 320 that way. So that's where I got that from. And so 0.320, and then that all equals 0. So it ends up that when we solve this, we get T1 plus T2 equals 400. All right. So now we have basically two equations, two unknowns. We know this, we know that. So we know that T1 equals T1 plus 3.248 T1 equals 400. So simple algebra, we get T1 equal to 94.157 and T2 equal to 305.84. Again, I carry a few extra places because I'm not in my final answer yet. And again, of course, those are newtons. So there's those, but I'm not done yet because ultimately I'm trying to figure out what is the moment required to cause this. So we know that E is the center, right? So the last thing we're going to do is sum the moment about E to 0. So if we go back and we look at this, we can see that T2 is going one way, T1 is going the other way. So T2 is going to be a positive moment, T1 is going to be a negative. So if we do that, we have the moment that we want to solve for plus T2 times 0.15 minus T1 times 0.15, all equals 0. And so if we go ahead and substitute that in, this number is going to be much bigger. So that makes sense. The moment's going to end up being negative in order for this to all equal 0. So once I substitute in my values here and here, I end up with moment equal to negative 31.8 Newton meters. Okay. So that makes sense because it's turning clockwise. Now, if you had wanted to go counterclockwise, you would have found out it would have been the same except this magnitude. So if you want to check it out, you can, but that's what it would have been. Okay. Now, this last problem, I'm going to walk you through it. It's not something I'd have on the final, but it's a good example of putting everything we know together into one problem. And for friction, actually, it would be a good final problem, but I think it's a little too much. Maybe some unsuspecting class in the future will get it. So here we go. Actually, let's go back to this. So here's the coup de grace, the culmination problem. So we have bucket A and block C are connected by a cable, passes over drum B. So the drum B rotates slowly counterclockwise, and the friction at all surfaces are 0.35 and 0.25. So that includes the bucket. So not the bucket, I'm sorry, the drum. So the drum has belt friction on it. Determine the smallest combined mass M of the bucket and its contents for which block C will A, remain at rest, B, start moving up the incline, and C, continue moving up the incline at constant speed. So the difference between B and C would be the difference between static friction and kinetic friction. So as we know that once it takes more effort to start C sliding, but once it's started, then it's going to take less mass to keep it moving because the kinetic friction is smaller. So how do we do that? So I'm going to walk you through it. I've already solved it, and I'm just going to walk you through the solution. Again, this is a little beyond what I'd expect on the test, at least at this point. So let's look at it. All right, so first thing I did was we looked at the actual drum. So we know that we have 90 degrees plus an additional 30 degrees of contact. So that gives us total 120, which is basically 2/3 pi, right? So it's not not the whole thing, it's just a third. So let's look at it. So we have our governing equation, T2 over T1, e to the mu times beta. And then we know that T1 is going to be mass times gravity. So we can substitute in for T1 mass times gravity equals mu to the 2/3 pi. And so of course we know that 120 is equal to 2/3 pi. Okay, so our first assumption is block C remains at rest, does not slide down, and that the cable slides on the bottom. So meaning that if it's going to move, it's going to slide, but we want it to remain at rest. So we assume that UK is 0.25. We have T2, again, from above, e to the 2 times, sorry if that's hard to read, 0.25 times pi over 3. And so 1.6881 is our mg. That gives us our ratio of T2. That's essentially what T2 is. It's 1.6881 times mg. So now we go to our block and we look at our block and draw the free body diagram for that. So remember that we're using the kinetic friction because this drum is turning. So there's cable is actually sliding on it as we speak. So that's why it's kinetic. So we go back to the block C and we look at it and we say, okay, if we take our free body diagram at the angle, we know we have a normal force, we have a friction force, because again, even though the cable's pulling it up, it wants to slide down. So friction, of course, goes against that. It's going to point up the hill. So, and I've just went ahead and tilted the axis so we know weight's always straight down, normal force is at this 30-degree angle, same with tension, same with friction. Now, we know that we're given the weight 100 kilograms, so we know we have the 980 newtons for our block. And so what we want to continue with is figuring out what tension 2 is. That's really what we need to know, because once we know tension 2, then we can relate it to the weight. So this is what we're trying to solve for. So if we sum the forces in the y, we know that N minus the mass of C, that's what MC is, times gravity, times cosine 30 degrees equals 0. And so normal force is equal to the mass of C times G cosine 30. And we also know that friction, the friction force, is going to be equal to 0.25 of the normal force, because that's our kinetic coefficient of friction. So if we sum the forces in the x, we know that tension 2 minus mg sine 30, again, this is mass of C. I should have put that in there too. Mass of C sine 30 plus friction equals 0. So tension T equals mass of C times G times sine 30 minus 0.35 mass of C G cosine 30. Okay. So now the reason we're doing that is because we use the kinetic friction for the drum, but the static friction is for the block. So that's the difference. So we use kinetic friction up here because the drum was turning, but the block we're saying is static. So we have to use the static coefficient of friction here. Okay, so that's the difference between the two. So then we go ahead and we solve, and we end up with a mass equal to 11.66 kilograms. All right. So we've already figured out what T2 is. So by solving this, we've determined that the smallest mass for this thing to stay still is 11.66 kilograms. And that's because we accounted for. Once we know T2, we know that's essentially what the force is that's going to be at T1. All right, so let's look at B. The smallest mass of the block starts moving. And so again, in that case, the smallest mass of the block starts moving is going to be tension 2 equals to mass times G times 0.35 2/3 pi. And therefore we get a relationship for tension 2. So again, in this case, we want it to start moving up the incline. So if we're moving up the incline, then what we want to do is friction is going to be the opposite. So now we have, again, mcg cosine 30 is n, just like before. Friction force is 0.35 mcg cosine 30. That's just the coefficient of static friction. And then if we sum the forces in the x, we know tension 2 is equal to the respective values. We plug in everything, we solve, and it turns out that 38.6 kilograms is the mass required to start it moving. Now, the only difference between it start moving and continue has to do with the friction, right? Because the friction drops. So if we just replace 0.35 with 0.25 in the appropriate place up here, we end up with 2.08. Basically take this equation and plug in 0.25 here, then we end up with 34.4 kilograms. So effectively it says that you need to take, it takes 34.4 kilograms to keep it moving. It took 38.6 kilograms to start it moving. And it took a value of 11.66 kilograms to keep it from sliding back. Okay, so I know I went through that one maybe a little quicker. I know there's a lot of little steps in this one, and it's I would say again, this is kind of the culmination of everything. So if you can solve, if you understand this one and can solve it effectively, then you're okay. Honestly, this isn't going to be on the final, so this level of friction. So this is more of an interest than anything. All right. So this is our last, as I said, our last lecture for the quarter. So I just wanted to say at this point, you should be comfortable with everything we've covered. We'll of course have a review session for the final, but otherwise there's no new material to cover. So congratulations, you finished statics and now you're ready to move on to dynamics. Thank you, and see you in office hours.